Okay, now that we're recording, everything with a big blue X through it, I probably would not give you on the exam. So the rest of it is what you would have. You'll have your y-axis labeled as your pH. You'll have your x-axis labeled as milliliters of something. That milliliters can be anything else. Okay? It can be amount, okay? Or equivalence. A lot of people are confused about the term equivalence. What does equivalence mean? Nobody? Okay. That makes it even a good point to bring it up. So equivalence just means how many equal parts of each. Okay, so we'll draw in a little bit more information on that in just a second, where we can actually look at some numbers. Then you'll have the curve across the top of this. Okay? And you would then have to go through and label this as best you can. So usually when I go through and approach these, I try and pick the extremes, because the extremes make a little bit more sense to me. If you start trying to interpret this curve somewhere dead in the middle, trying to determine pKa's, all that fun stuff, it's really easy to get misled, because if you've mismemorized something, you're kind of shot. So if we can kind of derive what's on here, we can probably pick it up a little bit cleaner. So where do you guys want to start? The extreme right or the extreme left of our curve? Your choice. Really doesn't matter. Okay, left. Good. I like the left better. So we look at the extreme left. Okay, I'm dropping a red dot. What can you tell me about that red dot? The pH is acidic. You can't tell me anything about milliliters of question mark, because I'm not on the x-axis yet. I'm only looking on the y-axis. So you can tell me I'm at an acidic pH. What happens as I move on to the x-axis? What happens to the pH? It goes up, which means it becomes, I'll accept less acidic, but more basic is a little bit easier to work with in this case. How do we get something to become more basic? Add base. So milliliters of question mark is milliliters of base. Right? You may see it written as base. You may be asked to specify base, or you may actually be given OH minus, okay, or NaOH. All of those are strong bases. We're not titrating a weak base in here, because that makes life hell. Okay, so we're looking at a strong base. What if our curve, just for kind of giggles, had started on the upper, oh, that looks horrible, but it's close enough. Okay. Now what are we adding in? We're adding in acid. Okay. So now, let's undo that. Let's come up with some symbols that we can address in here. Yeah?
Just a bit more basic, just what's the definition, like, to titrate, the verb, what does that mean?
So to titrate means to controllably add small volumes of one species to another.
Got it.
Okay? And you're looking usually at liquids, because it's easier to control those small volumes with liquids.
Yep.
Okay? So we know at that starting position that we are acidic. Okay, that was close enough. We'll just stay at acid. So now that we've got this information, I now actually want to interpret this a little bit further. I want to start to build a reaction equation. So reactants and products. If I'm starting here, I'm starting at my reactant. Okay, so what can you tell me about my reactant? What does it have to have in it? Has to have a hydrogen, because it's an acid. Right? Do we know what that H is attached to? No, there's no way we can figure that out from the curve. So what we can do is now just provide a generic symbol. I'm going to just call it HA. Okay? Doesn't matter what it is, but that's all we're saying. Okay? What's going to happen is that when we look at HA, as we slowly add base, what happens to HA? The solution becomes basic, but then what happens to the structure of HA? It dissociates, and what I'll end up with is A minus, where I've removed that hydrogen. Right. We're going to run into some interesting kind of questions here. You'll notice that I'll say H3O plus, and I'll put H2O over here, not saying I'm adding a base or a strong base necessarily. Because if I add a strong base, I'm not at equilibrium. I'm doing a reaction. And what I'm trying to interpret off of this curve is actually the equilibrium. Each section of this curve is a data point. That data point is at equilibrium. Okay. But to move to the next data point, I have to move out of equilibrium, do the little reaction, now record the new equilibrium. Okay, so every point along here is at an equilibrium. We add a little bit of base, it's out of equilibrium, we let it readjust to its equilibrium, and move forward. So when we look at our equation, what we're really just looking at is the dissociation of HA into A minus. Okay? So as our reaction continues along, so let's say we start with 10 HAs. Okay? And we add a little bit of base. What happens to the concentration of HA? Okay, so if we add one base, okay, the result is that HA is going to drop because the base is going to react with HA. So that becomes 9. What happens on the other side? What happens to A minus? Anything? It has to increase. Right? And if we're at a purely acidic environment, we're saying there is no A minus to start. But now that we add base, we're starting to convert HA into A minus. So with a small amount of base, HA goes down, A minus goes up. Okay? If we looked at our overall reaction, if we just added straight base to water, what happens to the pH? It should jump. It should become basic. Okay? But what happens in the case if we have a weak acid present? I add the base reacts with HA, what happens to the concentration of base? Goes back down to 0. Okay? So should the pH change? No. So what happens to our pH? You'll notice that it stays relatively flat. Okay? In a perfect world, it'd be perfectly flat, but we get all sorts of other dissociation factors we talk about in 152 we don't really need to worry about. But for the most part, it stays flat. Okay? So what's happening is HA is buffering the addition of base. Okay? So all we're saying by buffering is we're preventing a pH change. Okay? And you'll notice that when I'm phrasing that, the preventing I'm looking at is it's only buffering base. Would it buffer acid? So if I add more acid, is there any A minus to react with it? No. So I add acid, what happens to pH? Falls through the floor and it gets super acidic. Okay? So a solution that is just HA cannot buffer acid because there's no conjugate base to react with it. Okay? So as we start to move along this curve, our concentration of HA decreases and our concentration of A minus increases. Okay, until what happens? Okay, and this is where we can bring in our equivalence. Now instead of adding one molecule, I'm going to add one equivalent of base. What does one equivalent mean? A little bit less generic or more generic than 10. 10's a bit specific. Why'd you say 10?
Just same amount.
The same amount that we started with. The equivalent amount. There's our equivalence. So if we're saying we're adding one equivalent of base, really what we're saying is we're adding 10 molecules of base to balance out our 10 molecules of HA. Okay? Now what's the concentration of HA? 0. Because it has now entirely been reacted with the base. What's the concentration of A minus? 10. It's all shifted over. Now that we've done this, we'll record our pH. There's no more base to change the pH. Okay, so we'll still be slowly on this kind of increasing value. Add one more molecule. What happens to the pH? One more molecule of OH minus, of our base. The pH is going to skyrocket. There's no more any acid, or no longer any acid, to react with the base that we've put in there. So now we have a concentration of hydroxide. With that concentration of hydroxide, our pH is going to skyrocket. It's going to become very, very basic. Okay? That is happening at this point, the inversion point. Okay, if we look at the lower part of this curve, it's aimed upwards. If I look at the upper part of the curve, where's it aimed? Downwards. Concave up versus concave down. That inversion point is the point at which the concentration of HA is exactly the same, or the concentration of HA that I started with is exactly the same as the concentration of base I added. Okay. It is one equivalent of base. Most commonly, that point is referred to as the equivalence point. Okay, and this is where things can become a bit odd, as we'll see in a second here. So what we've got now is the equivalence point. At the equivalence point, what I'm saying is that the concentration of my acid that I started with initially, so I'm using that lowercase or subscript I, is now equal to the concentration of base that I've added. Or really the moles. It's not actually concentration, it's moles. Okay, it's strictly the amount, which is, yes, related to, but can sometimes be different from. Okay, so that's really what our equivalence point is. Well, can we get any information about our acid at that point? Okay. Well, that's where we can go back and interpret our Henderson-Hasselbalch. You'll notice that they've given you a pH. And this is where I said it was misleading. And if you remember back to 152, you might vaguely remember or have this assumption that pH equals pKa. Not always true. Where does pH equal pKa? At the half equivalence point, not the equivalence point. So the question becomes is what's going on with that? Well, let's take a look at our equivalence point, and let's take a look at our Henderson-Hasselbalch equation. Okay. Can we determine the pH off our curve at that point? Yeah, 4.01. We can't determine the pKa quite yet, because that would be something we would try and solve for. Plus, the log of the concentration of A minus over the concentration of HA. Right, so let's just use the numbers that we've got. At this equivalence point, what's the concentration of A minus? Assuming the example we just worked with. 10. Okay? So we could put that number in. What's the concentration of A minus? Or sorry, HA? 0. What's a number divided by 0?
6.
Undefined. Okay? So we've got a problem. At this equivalence point, you can't actually solve the equation. Okay? So that 0 concentration messes with everything. And that's, if you remember back to 152, when you get to the exact equivalence point, you have to do all sorts of extra calculations to account for this issue. Okay? So we cannot solve for the pKa at this point. What we were really hoping for is the expression that you guys just went through and said, come on, pen, pKa, whoops, let's stick with the same format, pH equals pKa. Well, for that equation to be true, what does this expression have to equal?
0.
0. Okay. For that expression to be 0, what does this have to be equal to?
It has to be the same. When you take the log of that.
It has to be 1, which means the concentration of A minus must equal the concentration of HA. Is that true at the equivalence point? No. At the equivalence point, what's true? The moles of HA equal the moles of strong base added. Not the moles of the conjugate base, but the moles of the strong base added. So we have to be very careful with what's happening at each of those points. When is it true that the concentration of those two things are equivalent? And yes, I intentionally use that word. At the half equivalence point. Okay? So to get to the equivalence point, I had to add exactly the same amount of base as I started with of my strong acid. What happens if I add exactly half of that amount of base? How much base would I be adding? 5. right? So let's erase those options again. We're adding to the half equivalence, so we could say 1/2 EQ for our equivalence, which in this case would be 5 molecules of strong base. What happens to HA? It reacts with the strong base, so it goes down to 5. What happens to A minus? It goes up by 5 from its starting 0 point. Okay, where did that 5 come from? Well, we reacted HA and turned it into A minus. So at the exact half equivalence, the concentration of HA equals the concentration of A minus. That now takes us to this pH equals the pKa. So that happens only at the half equivalence point. Okay? And this is, to me, one of the reasons why this is confusing. Because our equivalence point was the point at which our acid equaled our base. Our half equivalence point was the point at which our base equaled our acid. Did I just say the same thing? Yeah. But remember, when we talk about these things, we don't talk about them strictly as bases and acid. At the equivalence point, the initial concentration of my acid is equal to the amount of strong base that I've added. At the half equivalence point, the concentration of my conjugate base equals the concentration of my acid. Our equivalence point is based off of very specific terms. How much base have we added in comparison to how much acid we started with? Okay? And the base that we're adding is not the conjugate base. It's a strong base. So we have to be careful and not just skip steps and say, well, it's acid and base. Okay? You have to be very, very particular about what terms you're using to refer to each individual piece. So where would the half equivalence point be then?
Halfway between your first equivalence and 0.
So we look at the amount of base we've added to get to our equivalence point, and we now do exactly half of that, which I think is there. So that puts us at our half equivalence. Okay. At that point, I know the pH equals the pKa, which means I can now say the pKa for this acid is about 2. Okay, and I'm now at my half equivalence point. Kind of makes sense? And also at that point, I'm going to have to erase some of this stuff. We know that A minus equals HA. Questions about that so far?
Just don't understand, like, when you add 10 moles of, like, the strong acid, the HA, that's just, like, negligible? You can add, like, any amount?
We can start with any amount because what we're doing is looking at how it reacts with the strong base that we're titrating in. So the numbers I've picked here are random numbers to help us kind of deal with that, to actually associate things to it, so that we can then see those variations. But those amounts can be anything. That's why we talked about this equivalence. That could be 100. Am I going to be at the equivalence point by adding only 5? No, I'd have to add 50 to get to the equivalence point. Or sorry, the half equivalence point. Okay? So those numbers will change depending on what concentrations we've got, and ultimately they don't affect our interpretation of the curve. If I change the concentration of this, I'm going to have to add a whole lot more base, which means what happens is my pH, or this curve, is now just going to stretch for a longer distance flat line before it spikes. Because I have to add more of the strong base in to neutralize it out. So the concentration is irrelevant. We don't need to know those numbers. The only reason they're present here is to help us kind of sort of draw information into this.
At the second equivalence point,
Not there yet, but yes. We okay with the first one? I was waiting for someone to say, well, what about all the rest of the curve? Okay. Are we okay up to that red equivalence point? Okay, we now have a problem, because if we look at the curve, okay, if we just had HA, and I've now converted it all over into A minus, and I continue to add OH minus, what happens? There's no HA left, and the pH should skyrocket, and there's nothing that should stop it. It should go all the way up to its max pH with no variations off of that. If we take a look at the system, what happens? Spikes, awesome, that's exactly what we predict, and then, oh crap, it flattens out again. Okay. How can it flatten out? Okay. There has to be another acid present to neutralize that base. Okay. So there's two ways we could solve this. That means somebody threw two acids into this. Okay. You really don't want that problem. Okay. Because now you've got two buffers interacting with each other, and that's just going to be a mess. Okay. The other problem, or the other way to solve this, is that we didn't start with HA. What did we start with? We started with a diprotic acid. We started with H2A. There are two hydrogens that are acidic on that structure. One happens to be more acidic than the other. So that first one reacts, then the second one can react once we get to the proper, or once we've removed all of that first one. How does that change our reaction? Okay, well, if we start with H2A, then do I have A minus? No, what do I have now? HA. Okay. What happens as I add more base? Well, now we get A minus 2, because it's now lost yet another hydrogen. Okay, you'll notice again that I don't show the base in this, because the strong base being added is not at equilibrium. What we're trying to interpret is our equilibrium concentrations off of this, and it's how does that strong base get us to that point. Okay? So, we're going to have to clean some of this up a little. Let's see, how do I want to clean it up? I may regret erasing all that, but we'll see what happens. Okay? So now what happens is we're at this point. Okay? What things are present at that first equivalence point? Clean. So we want to go through and make some tweaks to all the information we've got written down there. Okay, we really have HA minus and H2A. We have H2A here. We still have moles of OH minus. There's actually another piece of information we can put at the equivalence point. Oops, I needed that still. What species of our acid, our organic acid, or our buffer, is present at the equivalence point? Is H2A there? No, its concentration is now completely gone. Is A minus 2 there? A minus 2 means I've removed another hydrogen. Okay. For that first curve, I'm looking at this first equation. What species is present? HA. The only thing present at that point is going to be HA. Okay. And in this case, HA minus. And the only thing to start our whole curve off was H2A. Okay. So now what happens? We add base. What does the base do? What does the strong base do?
Reacts with the other hydrogen.
Reacts with HA minus. So now the strong base disappears. The pH can't spike that much anymore. So we get, again, this kind of pseudo flat line. Right? Until eventually what happens? I've added enough base that now all of the HA is gone. Which means I'm now at the equivalence point. Why is this now further confusing? So we look at our curve. you'll notice that we have equivalence point written twice. Right? So it might be helpful to go through and label these as the first and the second. Should have been, well, I'll be consistent with it. Right? At the second equivalence point, what do we know to be true? It's going to be very similar to the things that we knew to be true when we dealt with our first equivalence. But we're going to have some things tweak off of this. What are the things that are going to tweak off? Well, our moles of HA minus initially will equal the moles of OH minus added. Pretty much the same thing as we had down below. What else do we know? What species is present at that point? It's just A minus 2. There's no more of any of our weak acid. We've now completely converted across to being just A minus 2. So we could call this our first piece of information, our second and our third piece of information, all labeled at that point. Hi. With the second equivalence point, can we make any conclusions about our pKa? No. What do we need to make conclusions about the pKa? The half equivalence point. So how do we calculate the half equivalence point? Half of the base added, okay, because that's what we're looking at for our equivalence, is how much base we've added. So we could look to our bottom, and that's how much base we've added. Where's the half equivalence? Interesting dilemma. If we run off the exact same thing we did for that first one, the half equivalence point, half the amount, takes us to our first equivalence point in this case. Okay, but is that really the half equivalence? No. Okay, because we've now shifted our focus to a new acid in a new environment. What we're looking at when we look for our half equivalence for the second section of acid is this is now the amount of base added to react with HA. This first section was not reacting with HA. There's no reason to look at that section. So now when I look for the half equivalence, I need to look at half the distance between my red line and my orange line, which will be somewhere about, it's probably straight on that line, somewhere about there. I now have a half equivalence point. What's true at that half equivalence point? The pH equals the pKa. Anybody notice a problem? What did we say was true at the other half equivalence point? Whoops, I didn't write it up there. I actually provided a number. The pH equaled our pKa. And we said that was about 2. Okay, so, wait, I said pKa is 2. What would I say the pKa was here? I would end up saying the pKa is about 6. So wait, for the same acid, I'm saying the pKa is both 2 and 6? That's kind of confusing. Are those pKa's referring to the same acid? No. One of those is referring to the first hydrogen in the structure. The other one is referring to the second hydrogen. So instead of just calling this pKa for both, that it's pKa3 and pKa6, was it 6? I didn't actually look at it. Oh, it is. We can call it the pKa2 and the pKa1. Okay? To kind of separate those two things away from each other so that we can now start to interpret them a little bit better. What else is true with the half equivalence? It's how we ended up finding out that we had the pH equal to the pKa. Concentration of, I want a little bit more than acid and base because there's too many acids and base floating in here. So we'd have the concentration of HA minus equal to concentration of A minus 2. Okay. All we had was a curve and the Henderson-Hasselbalch equation, and I've now flooded this slide with so much information it's ridiculous. Okay. All of this stuff is things that you guys need to be able to interpret relatively quickly off the curve. Okay. Most often what we're concerned about is what's the pKa. Okay. So if you looked at a curve, can I erase everything? Okay, I won't erase anything because there's a few people shaking their heads. Okay. What you would do is look at this curve, and you would immediately zoom in or change your focus to the half equivalence points. Because what's happening at those half equivalence points? I know something about my acid. I know pKa1 and I know pKa2. That gives me some interpretation. Taken a step further, at that exact point, remember when we talked about buffering? We said we're right down here at the very beginning with our H2A. It's the only thing present. I said H2A could buffer the addition of base. Because as I added base, what happened to the pH? It stayed relatively constant. But it couldn't buffer the addition of acid because there's no base present to buffer that, to prevent the pH from dropping even further. What is special about hitting a pH that's exactly the pKa? What happens if I add acid? If I add acid, the pH would go down. How much does it go down by at that point?
Matters on your strength of the acid.
If I'm right here and I add acid, what's going to happen? It's going to go down by how much? Almost nothing. Because it's a relative flat line. What happens if I'm at this point and I add base? It goes up by how much? Not much. So I can now add acids and bases to this solution, and the overall concentration of my acid or base stays relatively constant. Okay. That relative constant allows me to now control my reaction at those relative constant concentrations, and my structures don't change drastically with an addition of an acid or base. Because remember, if we switch from an acidic solution to a basic solution, physical properties drastically change. Because we could now move from, say, a neutral compound to a charged compound. And if it's charged, it's really soluble in water. If it's neutral, its solubility drops, becomes much less soluble. Okay, so a biological system wants to be able to buffer. If it cannot buffer, then a small change in the pH, a single hydrogen ion, can now take your blood from being liquid to being solid. Okay, we don't want that. Okay, so all of our biological systems are in some kind of buffer system, which means if I now want to go through and study those biological systems, okay, it's not very easy to stick a microscope up someone's arm and take a look at their bloodstream. What do you have to do? You have to draw blood. Okay? But as soon as you draw the blood, what have you now done? You've opened up Schrodinger's box and the cat's now dead. Okay? You've changed your environment. So what we would have to do is draw that blood out and put it into an environment that is as close as possible to where it was in the biological system. Which means I need a buffer. So when I pull stuff out of biological systems, I need to make sure I maintain that buffer system as close as possible to the natural environment. Okay? Because as soon as I change it, every observation that I'm going to make is going to be drastically different than what's happening in the bloodstream, okay, or in those cells. Yeah.
I just had a question with the equivalence point. If you originally started with 10 molecules of acid and you add 10 molecules of base, you reach your first equivalence point. But when you reach your second equivalence point, do you want to disregard from adding 10 molecules of base to originally get to the first?
So if we started with 10 of H2A, how many moles of base do we have to add to get to our second equivalence?
10.
Why 20?
Because it was only the half equivalent point of the second equivalent point. So you'd have to double it to get to your second answer.
If we add 10, moles of base, we now take all of our 10 of H2A and turn it into HA minus, which gets us to the first equivalence. If I now want to get to the second equivalence, what do I have to do? I have to add another 10 to push to the next point. Okay? So what makes these curves, particularly in biological systems, confusing is that almost all of them have multiple equivalence points. Each of those sections, that first section right there is a titration curve, acid to base. This section right here is a new titration curve, acid to base. Unfortunately, those two titration curves are on the same curve. So you kind of have to cover it up and ignore its presence when you go through and move it, which is one of the reasons why when you look at the axes, particularly sapling, instead of showing milliliters, they show equivalence. Because the equivalence is a little bit easier to interpret. Because if we move from 1 here as an equivalence, what's this equivalence going to be? The second equivalent. Okay? The half equivalence of our second equivalence is going to be half the distance between those first 2 points. Okay? Not the whole thing. Okay?
So from point 1 to point 2, you only added 10 more molecules of base to get...
You added an equivalence. So you have to be careful, a second equivalence. So if we say we start with 10, then to get to A minus 2,
You need 20.
you need 20. You need 2 equivalents. Okay? So I don't want you saying 20, because if I go through and do this and say that that's 5, it's not 20 anymore. Okay? But it is still 2 equivalents. The 2 equivalents in this point would equal
10.
10. 5 to get me to the first equivalence, another 5 to get me to the second. Okay?
So on an exam, if you asked us how much did I add to get to the second equivalence, can we just
I
keep
wouldn't
it
do
vague and write second and 2 equivalents?
So on an exam, which I probably wouldn't ask that question, but if that somehow showed up on an exam, what you would see it as is a multiple choice. Yeah, I wouldn't ask you that straight up in a short answer. This lovely curve with all this information on it, okay, I went through and tried to slowly work our way through it to kind of derive where everything is. The main reason being is if I had just shown you this all at the beginning, I would probably have panicked and would have said, oh crap, I got to memorize this. This question will absolutely show up on your exam. You do need to be able to interpret all of these individual things and draw conclusions from a titration curve. So I do expect you to be able to fully label the crap out of a titration curve. Okay? So your option is go back 40 minutes ago and slowly work your way back through the video to make sure you understand how it interprets, or you look at all this information up here and you memorize it. Okay? I don't care, well, I do personally care. Personally, I want you to be able to derive your way all the way through it. Okay? And realize these are posted online. Okay? The video is posted online, so you can skip to 38:30 in the video, and you'll have this image directly in front of you with this little spiel that I'm saying now. Okay? Questions about this curve?
We'll remember some common ion effects, right?
We're not going to talk about common ion effects.
Okay.
So now I'm going to delete everything. That little red point. What species is present? And I'll even be nice, and I'll give you the equation. H2A goes to HA minus goes to A minus 2. What is present at that point? Okay, well, clearly that was too easy. What is present at this point? Just HA minus. What is present at this point? We have HA minus and A minus 2. Both are present at that point. Which one's present in greater concentration? HA minus. Why? Our half equivalence drops us here. We're lower than that, which means we have a greater concentration of the acidic species. Okay? In general, how I interpret and go through these, oh, I just erased my equation. Pretend the equation's still up there. I look at it, I see 2 equivalence points, which means I have 2 acids. The most acidic point, I'm going to have H2 because I have 2 equivalents, acid. All the way up the top, somewhere up here, I'm going to have A minus 2. So I tend to jump all the way up to there. Okay? I don't need to jump all the way up to there. I can jump to right here. And right there, it's just A minus 2. Now I can backfill through. This has to be HA minus. Once I have that information, I can now start to jump around and say, okay, at the half equivalence, these two need to be equal to each other. That puts me in here. Okay, I know my pH equals my pKa. Okay, at the half equivalence point between these two guys, whoa, come back here. Okay, I'm just going to do it like this. I have a pH equals my new pKa, so pKa2, and I have a pKa1. Those are the big bullet points that you should be picking off your curve. Okay? And you will be required to use that information throughout the semester. All that other stuff I stacked on there, I do expect to show up. So if you take a look at the practice exam, one of the practice exam short answer questions lists a whole bunch of stuff. Some of it is nonsensical. You got to put it into the curve. Okay?
Are we going to see more than 2?
Yes. Okay. In fact, we will draw more than 2 theoretically later today. We'll see. Any questions with the titration curve? Actually, we probably won't see it today. So we already kind of alluded to this. We want a buffer, and with that buffer, we want the pH to stay constant if I add acid, and I want the pH to stay constant if I add base. Okay? Which means if I'm now looking at a whole bunch of different buffers, and I want to get to different pHs, I need to be careful with what buffer I select. So for instance, if I want a pH 1, does it make sense to use tris as a buffer? Okay. Where does tris buffer? About 8.3. Plus or minus a certain range off of that. But the 8.3, when we're at pH 8.3, we're at the exact half equivalence. It can buffer both directions. Okay? So 8.3 doesn't make any sense for a pH of 1. What buffer would be the best for a pH of 1? Phosphoric acid, because that gets us closest to that pH value. Okay? To get to a pH value of 1, if I'm using phosphoric acid, how do I get it to a pH value of 1? Because if I just use phosphoric acid and I get it to its equivalence point, I'm going to be at a pH of 2.15. If I want that pH at 1, what do I need to do? I will add a strong acid to it to get the pH to drop lower on its curve. Okay. What's going to be problematic with this? That's such a low pH that I'm probably not going to be able to buffer acid very well. Okay. I might be able to buffer the base a little bit, but buffering the acid isn't going to work very well. What happens if I move to pH 4? What might I want to use? This one's actually kind of tricky. We want to pick a buffer that has a pKa as close to 4 as possible.
Phosphoric acid.
Phosphoric acid is darn close, so we could pick phosphoric acid. Carbonic acid, ballpark, getting kind of close. They're roughly about the same. We could probably try either of those. What would help us decide one way or the other? Well, what's our reaction? What are we going to do to our system once we react it? Are we going to end up adding acid to it, or are we going to end up adding base? Okay. So once I'm at that pH, if I want to buffer so that it doesn't go up anymore, okay, I'll probably use carbonic acid. If I'm looking at a system where I'm going to be adding acid to it, I want to pick a system where it's going to buffer on the acidic end. The phosphoric acid is going to be a better choice. Okay? If you don't have a good choice, then you may just be stuck with what you got, and you just have to make the best decision you can, and you have to think about the rest of your experiment. What are we going to end up doing in the rest of the experiment? Okay? pH is 6. Carbonic acid is absolutely going to be our best choice there. It's for sure the absolute closest to that. Okay? Almost spot on. pH is 7. Okay? We're probably looking at C or D. Both of those are very, very close. 8. E or F. Okay? So we're using that information to help us decide on what buffer is going to work best, at least as a first approximation. When we're given a choice, we now have to decide on the rest of our experiment. So we now run into this issue of what other things should we consider when looking at the buffer. Okay? So carbonic acid tends to be a really good buffer system. Okay? But if I'm looking at how CO2 is processed in the body, CO2 is processed through carbonic acid. So if I use carbonic acid as my buffer, I'm now changing the concentration of one of the reactants in my reaction. Is that going to change my observation? Yeah. So I may have to decide that while carbonic acid is a great buffer, I can't use it for pH 4 or 6 because it's going to interfere with what I'm observing. So I'd have to find a different buffer. Okay? You'll notice that a lot of the buffers have these weird acronyms because they're crazy looking structures. Okay? So we just talked about a couple things that can affect our buffer choices. Okay? We'll just drop all those in there, or maybe we'll drop all those in there. We want a pKa that's close to our target pH. Okay, so a suitable pKa. We want no interference in the process that we're monitoring. So if for some reason our buffer is involved in the process we're monitoring, that's a bit problematic. We just want the buffer to sit there and stop acid concentrations changing. Okay? Do not want it involved in the reaction. Okay? We want a suitable ionic strength. It's kind of weird. What does that mean? Let's take a look at some random reaction. And we're going to be looking at a couple reaction equations here, so it'll be a little bit dicey. So let's say our reaction, we'll call it reactant, goes to our product, okay, but at the same time it releases an acid, gives off H+. Okay. Well, if we look at that equation without a buffer system, is the concentration of H+ going to affect this reaction? Look at Le Chatelier's principle. If I increase the concentration of H+, where's the equilibrium shift? Towards the reactants. If I'm only concerned about what's happening between the reactant and the product, I don't want the concentration of H+ to change. So I'm going to pick a buffer system where H+ does not change. Okay? So ionic strength. Here's my new buffer. I'm going to throw in my buffer so that it can react. Okay, we'll have A- and HA. Now remember it's equilibrium, it can go either direction. Okay, the ionic strength is saying how much of the buffer am I putting in there. So I'm going to hit right at the exact pKa, so I'm going to say there is 1 molecule of A- and 1 molecule of HA in my buffer system. The reaction runs once. It produces H+. 1 molecule of H+. That 1 molecule of H+ is absorbed by the A-. pH doesn't change. Reaction runs a second time. What happens? Produces H+. Where does that H+ go? Into changing the pH. If the pH now drastically changes, what happens? Now my reaction, I'm not monitoring just reactant to product, I'm monitoring reactant to product in the presence of acid. So I want to make sure that the concentration of these two species is high enough that any fluctuations in my overall reaction of acids and base concentrations are absorbed by the buffer. So the concentration of my buffer needs to be high enough that it can withstand small fluctuations in concentration of our acids and bases. Okay? This usually means you see something in 0.1 molar solutions. because most often we're usually running at very, very low concentrations for biochemistry. The other problem, let's say I add 50 billion of these. I'm going to say 5 billion because, well, there's 50 billion. And actually, let's change that around. Let's make it 50 moles of each of these. It's a massive, massive amount of that. Okay. We draw this back to just salt water. Okay, I got a container of water, I add salt to it. What happens? Dissolves. I add more salt. Dissolves. I add more salt. I add more salt. I add more salt. Eventually what happens? The salt stops dissolving. The solution has become saturated with salt. Okay, it cannot physically fit any more molecules into it. So if I pick that as my buffer solution, my saturated solution of salt, and I now try and dissolve my biological system in it, what's going to happen? I'm probably not going to be able to get the biological system in it because I've already filled all of the soluble sites within the water solution. So I can't be too low a concentration. I can't be too high a concentration. If I push to either extreme, I'm going to affect my biological system, and I'm not going to get observations that actually make any sense. Okay? So that's what we're talking about with this suitable ionic strength. It's the concentration of our buffer. Too low, we don't get enough of a buffer range, or not a range, but we don't get enough of a strength of a buffer. Okay? It can change pretty quickly. If it's too concentrated, it can now prevent the biological system from dissolving in it. Right? And if we can't get it into that system, we can't observe it. Solubility issues. This kind of goes back to the ionic strength thing. Okay? If we pick a buffer that happens to be organic, so we use an organic solvent, say hexanes, and we try and dissolve a biological system in it, what's going to happen? Biological systems are based in what phase? We are 80% water. What happens if we try and dissolve a molecule that's soluble in water in hexanes? It doesn't dissolve. So we get a solubility issue. So we want to make sure that the buffers we use don't introduce these secondary issues. Okay? The other thing that can pop up is this non-biological nature of the buffer, which is what we're talking about with the carbonic acid. If we're looking at carbonic anhydrase, it's the molecule involved in transferring CO2 into carbonic acid and backwards. Okay? I don't want to use carbonic acid as a buffer because that's going to influence the biological nature of my system. So a lot of the buffer systems we use are non-biological because we don't want them influencing our biological systems that we're trying to study. So that's why you see those terms. Oh, this is going to be ugly. Okay? Pipes, HEPs, and tris. Those are the acronyms for those goofy compounds. Okay? Because the names are too confusing. Questions about that? So, 5 big things behind how we choose our buffers. So let's have more fun. I got 2 buffers up here. Which one of these 2 buffers will best buffer at a pH of 10? Yeah, I know, it's a bit obnoxious. How will we go through and deal with this?
We guess, and if it's the wrong answer, you'll tell us.
Okay. To decide this, we really have to go back to our understanding of organic chemistry, and in particular, how we rank acids and base strengths. Okay? Because once we know something about their acid and base strengths, we can then start to predict which one's going to be closer to a pH of 10. Okay? So pH of 10 is going to be what? Basic. So what we're going to be looking for is our most non-acidic compound. Okay. I know, it sounds kind of weird, but we're in a pH. So if we're looking at H, we got to look at our acidic system. We can't really look at the basic system. You look at this compound. Both these compounds have some similar features in them. What would that similar feature be, number 1? Ring, I can kind of accept that. I would say the rings are a little bit off because this one is all carbons, and this ring, while it has the same number of atoms, has oxygen and nitrogen in it. That's going to change our chemistry pretty drastically. Yeah. We look at the end, we've got SO3H. Okay, what can you tell me about SO3H? It's a strong acid. What can you tell me about nitrogen? Nitrogens are bases. Very misleading to draw these structures. Because we put these into water, the first thing that's going to happen, we're going to lose that hydrogen, and we're going to drop the hydrogen onto our nitrogens. So these are really the species we're looking at. I'm not concerned about the pKa of the sulfonate, I'm concerned about the pKa on the nitrogen. Right? So we go through and decide between these which one is more or less acidic. Right, how do we decide that? Nope, it's the same number of hydrogens. Resonance is almost always the answer in organic chemistry. Unfortunately, we're not in organic chemistry. There's no resonance. That oxygen is the key. It has electrons, but those electrons aren't going to necessarily do anything because they'd have to donate in to stabilize our nitrogen. Okay, they can't donate in. What is that oxygen doing? What can you tell me is a property of oxygen in comparison to carbon? It's electronegative, which means it draws the electron density in towards it. What happens to this carbon?
Partially positive.
Oh crap, I've lost electrons, so what does it do? Pulls them from the next one. What does this carbon then do? Pull it from the nitrogen. Which means what happens to the electron density between the nitrogen and the hydrogen here? Gets weaker or stronger? Weaker, which means this compound is more or less acidic. If that bond is weaker, becomes more acidic. So the pKa of this compound is going to be lower. This one's our better buffer. Okay. As a rough approximation. I know, that's painful.
So when you say you're looking for a buffer at 10, you're looking for something that's less acidic to keep it at that?
So both of these are now going to be acids. We want the one that's going to be closest to the pH of 10. We do run into some issues because you'd have to know the pKa's of your amines, okay, which we'll talk about, I think, today. Your amines typically have a pKa of about 9. Okay? So if they're both sitting on the more acidic end of that, okay, we want the one closest to the pH of 10. So which one's going to be our option? The one that's less acidic, which puts us better at this one. Okay? Fun stuff. Blood buffering. You can go through carbonic anhydrase, super efficient enzyme. We can look at this overall system and think about what might happen to the pH in our lungs versus our muscles. So what are our lungs trying to do? Buffer what out of the system? CO2. We don't want CO2 in our lungs. The whole point is to get it out. So what's going to happen to our pH? Okay, if we're in the lungs, what should the pH be in our lungs? Okay, let's switch it. Let's go to acidic or basic. Okay. If it's basic, what happens to the concentration of H+? It goes down. Which way does the equilibrium shift? Towards the products, which means what happens to the concentration of CO2? Decreases. Which means the CO2 is now going where?
Out.
It's turning into this. When you exhale, what are you exhaling?
Air.
Gas. That's aqueous. If the pH if it becomes more basic, the concentration of H+ drops. Our equilibrium shifts to take CO2 gas and do what with it? Put it into our bloodstream. What do we want to happen? We want the CO2 to come out. So we want the CO2 as the gas phase. How can I make sure the CO2 stays in the gas phase? I make the environment more acidic. What happens if I increase the concentration of my product? Equilibrium shifts to the reactant. So the pH in our lungs is likely acidic, because that's going to help push the CO2 out of our bloodstream. What happens when we get into muscles? We're going to want the opposite. Okay, why? Because our muscles are generating CO2 potentially, and we want that into the bloodstream so that it can be transported to our lungs, and then our lungs can expel it. So depending on where we are within the body, our pH can change. And those subtle changes in pH can take random molecules, such as CO2, and either put them into an environment that we can get rid of, okay, expel from our body, or put it into our bloodstream that can later then be shipped somewhere else where it can be gotten rid of. Because what happens if our blood just, or our muscles just put out raw CO2 gas into our blood? We get air bubbles in our blood. What happens when air bubbles hit our heart? We die, okay? In most approximations. That's a bit problematic. Okay, so we want our gas molecules to stay dissolved in the bloodstream. The easiest way to do it is to convert them into another molecule that's water soluble. Okay? Then we can push them to an environment where it is safe to now release that gas, and that's where our lungs are coming in. Okay? So buffering is of incredible importance when we're looking at these biological systems, and more particular, looking at the pH changes within it. Okay? So the next question would be, would it make sense to use carbonic acid as a buffer?
Yes.
Okay? Carbonic acid is related in this reaction. Okay? So if I'm going to use carbonic acid, that's now going to change the concentrations of each of these species. Those species, if I'm studying the enzyme that's processing these, that enzyme is going to start to process the buffer. If it processes the buffer, am I studying the enzyme working in the biological system, or am I studying the enzyme working on what I fed it? Okay? I'm looking at both, which means what happens to the conclusions? We don't really know. Okay? So the buffer system that we would like to use here, even though carbonic acid is going to match the pH system perfectly, is not going to be a good choice, because I'm now physically altering the system under which our enzyme works. So I would have to choose a different buffer system with a similar pH, or pKa, because I still need to maintain that. But if I bring in a reactant that's involved in the reaction I'm studying, that's problematic, because now I'm altering that concentration, not the reaction itself. Okay? I'm kidding. We're not going to do any mathematics. If you really want to do mathematics, you can talk to me after class, and I can go through and we can work this problem with you. Okay? What do I expect you to get out of this? What do you think is going to happen to the pH? pH should go down, meaning it becomes more acidic because I added a strong acid of HCl. That's really all I want you to get out for this class as far as doing the calculations. Come up with those quick approximations. You can deal with the exact details if you need to in the future. Next part of this is looking at amino acids. We really only have 5 minutes to play around with this, so we'll probably start with this kind of activity tomorrow. I've only got 4 sets. No, it looks like I got 5 sets. So I'm going to toss a couple of these sets out so you can take a look at them. I will post the document that I used to make this, because on one side you've got the name and the 3-letter code, and on the other side you have, I don't know which one was which. And on the other side you have the structure.
Hey, that reminds me, on the test, do we have to actually know,
Yes.
like, the compound name, or are you going to give them to us in abbreviation?
So what we're going to do here is we'll talk about some of the structures of these in a little bit tomorrow. But we got our list of common amino acids, and I will backtrack to all that information. We've got our list of our common amino acids. There are 20 of them. Depending on who you talk to, sometimes you'll see 21, but there's 20 primary ones. What I expect you to do is memorize 5. Okay? It's not just the easiest thing. Okay? Memorize 5. Within that memorize 5, name, 3-letter code, 1-letter code, structure, and classification. Okay. And for those of you going, oh my God, that's a lot. You're supposed to memorize all 20, right, in all fairness. Right, so here's our activity. I'm going to have you work on classifying these. So take a look at those structures. We talked about intermolecular forces and what intermolecular forces can do. And we want to come up with classifications for these amino acids. So talk to the people around you with the group of stuff that I tossed down roughly within each individual section. So you may have to turn around. And start coming up with how you would classify them. Ideally, don't cheat and look at the book or think of things that you've memorized before. But I want you to come up with your own classification system that you guys agree on, okay, for each of those things. So some ideas that you can go through and do. Don't worry about the models at this point. Look at the classifications. So ideas, polar. Is it acidic? Is it basic? Is it neutral? Those kind of classifications. Okay, and come up with as many classifications as you want to go through and process that. Okay?